Go ahead and turn to section 1.7 of your notes. By the end of the lesson, you'll be expected to find inverse functions, evaluate inverse functions, and identify the domain and range of inverse functions. Inverse functions. Given a one-to-one function, f of x equals y, we write its inverse as f inverse of x equals y. And a quick warning, this is not exponent notation. F inverse of x does not equal to 1 over f of x. It follows that if we compose a function with its inverse, like this, we end up with just x. Similarly, if we compose the inverse and the original function, we still end up with x. This can be very useful when we want to verify if two functions are each other's inverses. Now, the domain of the inverse function is the same as the range of the original function. And the range of the inverse function is the same as the domain of the original function. Now let's look at example 1. Example 1, determining whether functions are inverses of each other. Given that f of x equals 1 plus 3 over x and g of x equals 3 over x minus 1, determine if f of x and g of x are inverses of each other. Also, find the domain and range of both functions. So let's start by determining whether or not these are inverses of each other. So let's label that by the number 1. And let's compose these. So we write f of g of x equals 1 plus 3 divided by g of x. So if you notice, I'm replacing the x in the original function with g of x. So now we can write out what g of x is. We have 1 plus 3 divided by x minus 1. Now we have 1 plus 3 over 1 times x minus 1 over 3. If you are rusty on how I get from here to here, please review fraction division. As an aside, if you have a over b divided by c over d, this is equal to a over b times d over c. So let's keep going. I end up with 1 plus, and if you notice, 3 divided by 3 is 1. So these go away. Again, canceling out is just shorthand for division. So remember, you just divided by 3 to get 1. And then 1 times anything is just 1. So we end up plus x minus 1, and we end up with x. It looks as if these two functions are inverses. So as an exercise, on your own, verify that g and f are inverse functions by simplifying this right here. Now let's discuss the domain and range. Let's label this 2. So here I have f of x, its domain, and its range. And here I have g of x. So if I want to know what this range is, I need to find this domain. So let's kind of make this look a bit like a table here. And what is the domain of f? So I know that I don't want this to equal 0. And by this, I mean this x. It is in the denominator, so it cannot equal 0. So our domain can be written as the set of x, such that x does not equal to 0. Or you can write this in interval notation by going from negative infinity to 0 and gluing that with a union symbol to 0, infinity. So I know that this domain is going to go here. It's going to be the range of this function. So this is the set of x such that x does not equal to 0. Or we can write this as negative infinity to 0, union 0 to infinity. Now, what is the domain of g of x? And if you recall, g g of x is equal to 3 over x minus 1. So we don't want this entire denominator to equal 0. So let's solve x minus 1 equals 0. So if we add 1 to both sides, we end up with x equals 1. So our domain here is the set of all x such that x does not equal 1. Or this can be written as negative infinity to 1 union 1 to infinity. And then, of course, this domain here is this range. So that means my range here is the set of all x such that x does not equal to 1 or negative infinity to 1 union 1 to infinity. So if you're asked to find the domain and range of a function and its inverse, the easiest thing to do is to find the domain of both the function and its inverse, and then remember that this function, the original, will have the range that's equal to this domain, and this function here will have a range that's equal to this domain. Now go ahead and turn to the next page of section 1.7. Example 2, interpreting the inverse using a table. A function d of t is given below. This table shows the distance in kilometers of the International Space Station, ISS, as it travels in seconds. Interpret d inverse of 1150.5 and d of 60. So let's see, we have d inverse 1050.5. Where is that on our table? That's right here. This would equal to 150 seconds. And we can interpret this as it took 150 seconds for the International Space Station, ISS, to travel 1,150.5 kilometers. Now let's go ahead and find and interpret d of 60. And where is this on our table? That would be here. This is equal to 460.2 kilometers. And we can interpret this as it will take 60 seconds for the International Space Station to travel 460.2 kilometers. The key to remember is that if you start with the inverse, in this case, you're popping in kilometers, so this is a distance, and you should be getting out seconds. If you're using the original function, you're putting in seconds, and what comes out is kilometers. So the main point is that you understand what is going in and what is coming out of this function and its inverse. Next, let's look at example 3. Evaluating a function and its inverse from a graph. Here I have a graph of g of x. I want to find g of 5 and g inverse of 1. So this is my original function. So this g is original function. And remember, this would be our x value. So this here is the input. So let's find the output when we have an input of 5. So here's 5 on the x-axis, and let's follow this up until it intersects with the graph. And it looks like it intersects here at 5, 3. This tells me that g of 5 equals 3. Next, let's look at g inverse of 1. So this is our inverse function. And this here is the output of g of x. So it's the output of the original function. What this is asking for is g of x equals to 1. For what x value will my function g equal to 1? So let's find the output of 1. Let's follow this all the way over until it intersects our graph. And that occurs here at 3. This tells us that g of 3 equals 1. Or if we write this out in the original notation, we have g inverse of 1 equals 3. So we have just evaluated a function and an inverse using a graph. With that, let's turn to the final page of the notes for section 1.7. Example 4, finding the inverse of a function. Given that f of x equals 3 minus the square root of x plus 5, find f inverse of x. Then we're going to find the domain and range of both the function and the inverse. Finally, graph both the function and the inverse on the graph provided below. So let's take care of the rest of these steps first. So first, let's find f inverse. So let's make this number 1. So we can write this out as y equals 3 minus the square root of x plus 5. That is our original function. This is our original function. And now you're going to want to swap your x and y values. So you're going to swap x and y, then write this as x equals 3 minus the square root of y plus 5. Now you're going to solve for y. So we have x minus 3 equals negative the square root of y plus 5. So we have 3 minus x equals the square root of y plus 5. I only did this by multiplying both sides by a negative 1. This became positive, this x became negative, and this negative 3 became positive. Now let's go ahead and square both sides to end up with 3 minus x squared equals y plus 5. Finally, I have 3 minus x squared minus 5 equals y. And for this, I subtracted 5 from both sides. This tells me that f inverse of x equals 3 minus x squared minus 5. Now let's find the domain and range of both f and f inverse. Let's make this number 2 here. So let's start with f of x, and here is f inverse of x. And of course we want our domain and our range. I want to make sure I have enough space, so I'm scooching things over a bit more than I originally had. So this is 3 minus the square root of x plus 5. What can we never have inside of an even square root? We can never have a negative value inside of an even square root. So we want to solve x plus 5 is greater than or equal to 0. And since I'm going to need more space, if you notice, I'm just shifting things around a little bit. So let's subtract 5 from both sides. X is greater than or equal to negative 5. So our domain is negative 5 to positive infinity, where the 5 is included, and this is interval notation. you notice we just, if you notice, we want -5 to be the smallest possible input and every other input to be larger. So of course, now I know what the range of my inverse function is. Its range is -5, infinity. Okay, with that, let's find the domain of f inverse of x. We have 3 minus x squared minus 5. So I know this is a parabola, and let's rewrite this a little bit. I can rewrite this as -1 times x minus 3 quantity squared minus 5, which just becomes x minus 3 squared minus 5. I know my vertex is going to be at 3, -5. So let's look at a really rough sketch of this right here. 1, 2, 3, 1, 2, 3, 4, 5. Here, -5. And this is kind of what this parabola would look like. Something like this. But of course, we aren't going to have both sides of this parabola. We can only have one side of this parabola. Let me scooch this over so you can see this better. And which side will that be? Because that will help us to determine what our domain is here and our range is here. So let's do a quick rough sketch of our original function. And I'll make this in a different grayish shade. Now we have the graph of the square root of x plus 5. That means it'll be shifted to the left by 5. That's 1, 2, 3, 4, 5, -5. And it will also be shifted up 3. 1, 2, 3, +3. So this graph should look somewhat like this. And we want these graphs to be symmetric about this line here. Y equals x. That tells me that we're only going to need this side right there. Because then I could reflect these and end up with a mirror image. This curve up reflected would curve here to the right. Now I can be sure that my domain is from -infinity to 3. This coincides with what we see on the graph. If you notice this blue function, if we're looking at the values vertically, we can go as low as -infinity, but as we go up, we have to stop at +3. So my range of my original function is from -infinity to +3. Now let's go ahead and graph all of this. F of x is equal to 3 minus the square root of x plus 5. And f inverse of x is equal to 3 minus x squared minus 5. So once you have your axes sketched, you can start by sketching an f of x, and let's sketch this one in green. So typically, the square root function is graphed like this. We have these points here. Since the square root of 1 is 1, the square root of 4 is 2. And this is what we typically look like. Now let's translate this. We know we want it to be negative, which means it has to be down here now. We know we want it to be negative, so I'm going to translate these points. Instead of 1 positive 1, I have 1 negative 1. Instead of 4 positive 2, I have 4 negative 2. So this is the square root of x. This is y equals a negative square root of x. And now we have to take into account our translation. We want to add 3 vertically and then shift to the left by 5. That means this point is going to go up to 1, 2, 3, and then over 5 it'll be here. And then we want this point, 1, -1, is going to again go up by 3, 1, 2, 3, and then shift over -5 to here. And then finally this point, let's shift it over 1, 2, 3, 4, 5, and up 1, 2, 3 to here. We can keep going. Let me scooch this down so we can find a few more points. Before we do that, I'm going to go ahead and delete this. So we know we have a few points already. And so I know I had -1 and I got +1. Let's look at what happens to 0. Actually, 0 won't give us a nice value, so how about we do 4? At 4, we're going to add 4 plus 5 is 9. The square root of 9 is 3, so we end up with 3 minus 3 is 0. And that gives us enough points to sketch out a very nice version of this graph. So this is our graph of f of x here in green. Now remember, we're going to want to reflect all of these points across the line y equals x. And so this here is the point, -5, 3. Here's the point, -4, 2. Here's the point, -1, 1. And here's the point 4, 0. And so we want to swap the coordinates of all of these points, because if you remember, the domain becomes the range. So now all of these domain values are in the range, and all these range values become a part of the domain. So what does that look like to us? Instead of 4, 0, as I have here, I have 0, 4. Instead of -1, 1, I have 1, -1, and I have 2, -4, and 3, -5. So let's go ahead and sketch this out. So at 0, I have 4. At 1, I have -1. At 2, I have -4. And at 3, -5. And this gives me the left side of a parabola. Finally, notice these look like mirror images. You could reflect them about this line here, y equals x.